So in this unit, guys, we are going to look at some applications of the equilibria that we've been studying for the past two units. In this unit, we'll start off by studying buffer solutions and see how we can use the idea of a buffer solution to study the pH changes that occur with the titration of a weak acid or weak base by a strong base or strong acid, respectively. The next thing we're going to go into is solubility of ionic compounds, and we'll also talk about the formation of these things called complex ions. So to start off with, we're going to look at acids and bases, and just kind of a quick sample here. This is a problem essentially from the last unit, and the question is, what's the pH of a 0.5 molar solution of acetic acid? As usual, we're given the Ka, so we can set up the Ka equilibrium. We set up our ice table, and we solve for x, and we will get a pH of 2.52 for that, as you can see there. Now, something interesting happens when instead of having just a half molar solution of acetic acid, we have a half molar solution of acetic acid that also contains 0.2 molar sodium acetate. Now, you're going to see this fairly often, just as you did in the last unit. These ionic compounds that have, this weak base as an anion, and again, you guys have to recognize that the sodium is not really going to do much here, but this acetate will act as a weak base, and more importantly, it also is involved with this Ka equilibrium for acetic acid. So when we make our ice table, we'll have a half molar concentration of acetic acid, but now we also have a starting concentration of 0.2 molar for acetate. We make the ice table, we solve for x again, and you can see how much the pH has changed just with the fact that we have acetate. The acetate essentially shifts the equilibrium position more to the left here, which means that some of this will have to be used up. The concentration of H3O plus won't be as high, and we'll have a pH of 4.35 rather than 2.52. So practically speaking, the effect of having a weak acid and its conjugate base in the same solution is the pH of that solution will be around where the pKa of the acid is. So, if you guys are really curious, you can calculate the pKa of acetic acid, and you'll see, it's within this range, and we'll make use of that fact when we go to design buffer systems. So, speaking of buffer systems, this is the application of the common ion effect. A buffer solution is one that contains both a weak acid and or base and its conjugate. So the example here is hydrofluoric acid and sodium fluoride. Hydrofluoric acid would be your weak acid, this fluoride ion is your weak base, and we'll put those in the same solution. Now, what we'll notice, and I'll show you example calculations to prove this, is that the buffer will resist changes in pH. So if we add an acid or base to a buffer solution, the pH won't change nearly as much as it would have without any buffer system set up if you were just adding the acid or base to just, say distilled water. Now, the reason why a buffer works the way it does is you have, again, both an acid and a base in that solution. So in this hydrofluoric acid sodium fluoride buffer system, if we add an acid, we're going to add H plus ions to solution, but there's that fluoride ion there that can react with it. And because H plus is a very strong acid, it'll react totally with fluoride to form HF. And so this fluoride ion, as long as you have fluoride ion there, the H plus will be used up. At least most of it will be. If we add a base, then what happens is that this hydroxide we're added, a lot of it will be used up by the HF to go in this direction to form F minus. And so we have a weak base and we have a weak acid both in solution that can react with any H plus or hydroxide that we add to it, and it really does stabilize that pH. So a little sample calculation to show you what I'm talking about. Say we have a buffer system and we make it by having a solution that contains 0.15 molar ammonium chloride. Again, this is the important part here. This ammonium is our weak acid. Not sure why it's going to chloride. But anyway, this ammonium's our weak acid, and then the 0.3 molar ammonia is our weak base, and we want to know what the pH of this buffer is going to be. This is a very similar calculation to last unit. We just have to remember that initially, we have this whole common ion effect thing going on. So we'll have starting concentrations for both ammonia and ammonium. Now, because I'm given the Kb, I'm going to write the chemical equation corresponding to the Kb. In other words, the ammonia will accept a proton from water to form hydroxide. So I set that up, set the ice table, solve for the POH, and the pH I would get is 9.56. Okay, fair enough. What's interesting though is what would happen if I add 0.1 grams of HCl. Now I apologize for the kind of the unusual measurement of HCl. Usually we would use moles or molarity, but I don't know, I guess I was feeling saucy when I wrote this problem. But if you do the calculation, you'll find that the molarity of H plus would be 0.110 molar HCl. This has a pH of about 1. Okay, so if there was no buffer set up and we added this much HCl to that volume, we would have a pH of about 1. However, we do have a buffer set up, so let's think about what's going to happen. To get this pH, we first consider stoichiometry. So the ammonia, as I was saying, our weak base here will react with any of this excess H plus that we added, and it's going to go in one direction, so I made kind of an IC table here, and set that up, and the H plus reacts with NH3. As long as I have NH3, I'll be able to handle any H plus I added. If I add too much H plus, if I add, say, 0.31 molar, okay, the concentration of H plus is 0.31 molar, then I will run out NH3. My buffer, it says that we overload the buffer capacity. So buffers have a capacity which is dependent on the concentration of the weak acid weak base. That's how much, that determines how much H plus or hydroxide you can add before you overload the buffer. However, it doesn't determine the pH. Okay, the pH of a buffer doesn't really depend on the absolute concentrations of our weak acid and weak base. So kind of return to this problem, we set this up, and we'll find that after this reaction, we'll be left with 0.19 molar NH3 and 0.26 molar NH4 plus. We now go, and I'm going to consider this Ka equilibrium for ammonium, and use these as our starting concentrations. We use this as our starting concentrations. Calculate the Ka for ammonia from this Kb of the ammonia, and you solve for X, you solve for pH, and you get 9.11, which is a lot different than this 0.11 molar, or the pH of 1 you would have gotten with this without the buffer, and fairly close to this 9.56 that we started with before we had any HCl. So we had HCl to this buffer, and we just changed that pH by a little bit, and that's the power of buffers. It really does help to stabilize the pH of your solution, which is very valuable. It's valuable in a lot of biological systems, actually, where the proteins and metabolic processes would stop if you go outside a certain pH range. So that's what I had to say about buffers. If you guys have any questions, I'll be happy to take them in the next class.